As part of my series on weak interactions, I wanted to discuss 15 reasons mu and tau neutrinos don't exist. And the first point is mu particles are mesons, not leptons. And this is something that you probably never heard in school. But back in the 60s, it was discovered that a mu particle can be accounted for as a relativistic positronium pair, electron-positron in relativistic orbit, around an electron. And that has the mass of a muon. And a relativistic positronium pair by itself has the mass of a neutral pion. And I did a couple of videos on this, I'll link below. But this research has been suppressed because it changes the whole idea that there's 3 tiers of lepton. And if you continue this, too, tau particles are mesons, not leptons as well. If you study the Onium theory that I've developed of particles, you realize that the mass of a tau is equal to 2 kaons in a relativistic orbit around an electron or positron. But these kaons are in a reduced energy state that would occur if you had a pion orbited by another pion, rather than 2 pions in orbit, which would be at the higher energy kaon state, the normal kaon state. And so I did a video on that as well, and I've done papers on this that I'll link to below in the comments. So we're really dealing with the situation where if mu and tau particles are mesons, then they would each have to have their own neutrino. And every meson would have to have its own neutrino, which of course is not a viable elementary model of physics in any sense. You can't have hundreds of mesons have hundreds of different elementary neutrinos. It makes no sense. So there can only be 0 or 1 neutrino. That's it. We can't have more than one in any elementary model of physics. And 0, of course, would be more fundamentally simple. So 5. Weak interactions are initiated by quantum fluctuations. And I discussed that in some recent videos where electron-positron pair mostly, but also proton-antiproton pairs of quantum fluctuations can interact with particles, causing protons to be turned into neutrons and causing neutrons to decay into protons, releasing an electron. And that basically all the forms of beta decay that are the principal forms of weak interactions that we study can be accounted for by these quantum field interactions. And 6, the quantum fluctuations contribute energy to the interactions. For example, when a proton forms a neutron, the neutron has the mass of a proton, an electron, plus 782 keV of energy. That energy has to come from somewhere. And if you have an electron with enough energy and you accelerate it into a proton, that's one way to form a neutron. But in many cases, it forms at lower energy, and somehow the electron jumps inside the neutron with enough energy to form, jumps inside the proton shell and forms a neutron. And in case where the electron has lower energy, and there's been an experiment done by Sternglass as well, where at 35 kilovolts acceleration he was able to produce neutrons. He didn't need 782 keV of energy in acceleration to form neutrons. And in order for that to occur, the quantum fluctuations themselves have to contribute the energy that's necessary to form the neutron. And so that changes the model with respect to neutrinos. Neutrinos were originally devised as a way to account for the energy difference between the range of beta decay energies that the electrons or positrons from a decay process have a range of energies, not the fixed maximum energy, not this 782 keV, for example. And so they said, well, the neutrino carries away the rest of it. Well, they got it backwards. It happens at the front end of the interaction. And because it happens at the front end of the interaction, initiating the interaction, the quantum fluctuations contribute the energy. And then 7, quantum fluctuations carry away excess energy, momentum, and angular momentum. So when you have a decay interaction, you don't have neutrinos carrying away energy, momentum, and angular momentum, if there is any. You have quantum fluctuations doing it. And in that case, you don't need neutrinos in the theory at all. But I'll talk about that more in my next video on why neutrinos don't exist. So 8, conservation of angular momentum, releasing a mu or tau neutrino requires 2 rotating particles. You can't get angular momentum from a point particle. Point particles don't have angular momentum because they don't have dimensions. So you have to have a particle with dimensions and mass or some form of energy in order to get angular momentum. And in particular, in order to get the angular momentum of a relativistic positronium, you have to have 2 particles. And 9, electric neutrality requires that you have an electric charge dipole, because you need a dipole that is neutral to account for any energy momentum or angular momentum that's carried away, or any other property that's being conserved. So 10, the angular momentum must be carried away by a series of quantum fluctuations. And 11, these quantum fluctuations are electron-positron pairs. Well, it's possible some could be anti-proton pairs as well. And basically we have a form where if these pairs are rotating consistently in the same direction, you can have a series of pairs that conserve angular momentum. Although the successive dipoles would need to rotate in the opposite direction so it doesn't produce a magnetic field as well as a angular momentum, unless an electric field is being conserved by the quantum field. And through these types of processes, it's possible for the quantum field to preserve all types of interactions. And in their momentum conservation, this can propagate in a direction. And this type of interaction can interact with other molecules and be detected, as we've detected. So neutrino detection experiments can be picking up quantum fluctuation interactions and quantum field propagations of conserved energy and momentum. We don't have to have a particle that does that. The quantum field covers it. So 13, the mu neutrinos, which aren't really neutrinos, carry the angular momentum of an electron-positron pair. And 14, the tau neutrinos that aren't really neutrinos carry the angular momentum of the cation pair. So there's a different amount of angular momentum, and that's why we see different neutrinos. An electron neutrino doesn't have to deal with the angular momentum of the muon. And then the tau has additionally higher angular momentum. But there are many other forms of mesons that have different levels of momentum that have to be conserved. And the only way for that conservation to happen is in a way where there's quantum fluctuations. You can't account for conservation of all the properties of particle decay using 3 neutrinos, or especially not 1 neutrino. And so if all of the conservation of energy, momentum, angular momentum, spin, etc. is done by the quantum field, then it's better to just have a theory that says it's all done by the quantum field. So 15, the quantum field does what neutrinos supposedly do. We don't need mu and tau neutrinos, and they don't fit in a simplified particle model. Well, I hope you enjoyed this video, and if you did, please like it and share with your physicist friends, and subscribe to see my next video. And if you would like to learn more, as I said, I link to papers below. I discuss this in 3 of my books, and in the greatest detail in my book, Goodbye Quarks, the Onium Theory. And these books are for sale on Amazon. I put links for those below. And because I'm a retired independent researcher, if you buy one of my books, that helps me in my retirement, helps me to continue to do more research and to produce more videos. And so I appreciate the support if you'd like to buy one of my books. So thanks for watching.